Good afternoon, everybody. I would like to start today's lecture about Avr Instruction Set. We will discuss the Avr Instruction Set for the Atmega 328. So this microcontroller has an 8-bit microcontroller. Okay. So of course this means 8-bit microcontroller that the data bus is 8 bits. So if you want to visualize this a little bit, we can draw some simple architecture for the Atmega 328. It's very simplified. So we have an ALU. This ALU does the arithmetic and logical operations. It has two inputs of 8 bits and one output of 8 bit. So we start with the ALU since it's the core of the microcontroller, and then what we need to do is we need variables. So in order to have variables, we store them in registers. So as in any programming language, we have variables, and these variables go into registers, and of course these registers should be 8 bits. Okay, so it's a register like this. It has D7, D6 all the way to D0. This is the least significant bit and this is the most significant bit. So of course we have more than one variable, so we need more than one register for that. So more than one variable implies we need a memory for that, and the first part of this memory is called is used to store the registers, and these registers will feed the ALU with all the variables it wants. So this is, I'm gonna call this general purpose register. So of course, let's say I want to add two numbers. I have 5 here and 6 here. 5 will come from here, 6 will come from here. They will be added, and of course the result should be saved again in our variable list. So general purpose registers are 8 bits. Of course I'm gonna abbreviate them with GPRs, are 8 bits, and in the case of Atmega they are 32 registers to be used. So the GPR part of the memory starts from, this is R0, R1, and goes all the way to R31. Of course, since we start from 0, the total is 32. So these registers are our variables, and these variables will be used to do simple computations such as addition, subtraction, and any logical operations. So let's start with the first instruction that we will use, which is the Ldi instruction. So the Ldi instruction, let me write this here. So first instruction, Ldi, okay, which is load immediate. So the Ldi instruction is used to command the controller or the microcontroller to do a specific task, which is loading a constant into this GPR. So Ldi, what it takes is as follows: Ldi RD, K. Okay, K is an 8-bit constant. Of course, could be positive or negative. We have also the destination register. So this destination register is a GPR. However, we cannot place anywhere in the GPR. As you remember, I said the GPR consists of 32 registers, starting R0 to R31. So D, subscript D, should be between 16 and 31. We are not allowed to place in the first 15 registers. So this is R15 and this is R16. So we are not allowed to place in any of the first 16 registers. And this is primarily because of limitation in the instruction set. So as we said, that since at Mega 3 to 8, the microcontroller we are investigating is 8 bits. So the instruction is 16 bits. And in the next lecture we'll discuss all about how to transform this instruction into machine language. So let's take an example. So let's say I want to place some values in R16. So simply I say LDI R16 0x05. So this places inside R16 the value 5. Now let's say I want to place another value. We have LDI R17 0x06. So this means I'm going to place in R17 here the value 6. So this is the first step or the first instruction that we're gonna take, which is placing constants inside of the general purpose registers. So these are the GPRs. Okay, and this is just a part of the memory which is used to communicate with the ALU. Of course, if I want to add, subtract any number, the number should be first in the GPR. So a very important note here: to do any operation with the ALU, the values should be placed in the GPRs. And the way we do this is, of course, using LDI. So this is why we start with this instruction. So let's say I want to add those two numbers. I first have to place them inside the GPR before actually doing any sorts of additions. So now if I want to add those two numbers, I can use the add instruction. It takes two parameters, two registers from the GPR, RD and RR. Okay, D can be any register from 0 to 31, and RR and R, small r, can also be between 0 and 31. So in this case, if I want to add 5 to 6, I can do as follows: LDI R16 0x05. Remember, this is 8 bits. Can't go more than 8 bits. 0 0 0 0 1. And I have LDI R17 0x06. And then I can do the add instruction, which will add to R17 R16. So eventually R16 will be 0x05 and R17 will be 0x05 plus 0x06 equals 0x0b. Okay, so this is the add instructions. Now we have some notes about representation in LDI. So with LDI, if I want to load a decimal, I can do something like this, 50. In this case, the decimal value of of 50 will be in R16. If I do something like LDI R16, 0x5, what happens is that R16 will be equal 0x05. Doing something like illegal or wrong, like LDI R16 0x36f, we know this is more than 8 bits, so this is wrong. Also doing something like LDI R15 0x05, this is wrong because of R15. So we cannot actually use, as I said before, registers less than 16, and we cannot use more than 8 bits for the constant. Now, if I want to go more into details in the memory, the data memory of the AVR or the Atmega 328, so let's discuss the data memory of Atmega 328. So as we said, the first part, it consists of 3 parts. So the first part is the GPRs. Okay, I draw it here, and we have from R0 to R31. The address is 16 bits. This means that the starting address here will be 0x000, and the terminating address will be 0x001f. This accounts for 32 registers. These are the GPR. So GPRs are used for general purpose. They are my variables. The second part is the I/O, the input-output registers. As we know, all microcontrollers has inputs, outputs, and has some special registers like special functionality like a timer, like an interrupt, all of these special functionality. So we have another part which is the special purpose register. So with the special purpose register, they are specific registers that have specific functionalities. Think of them as your settings. So how you want your microcontroller to operate. And these will start directly after this from 0x00 to 0, and we will go all the way to 0x005f. They're around max of 64 special function registers. Now, to elaborate more on special purpose registers, they are, as I said before, the inputs, the outputs, the ports, the pins, how I can access the pins in a microcontroller, how can I access all specific functionalities that are characteristics of this microcontroller. The third part is the SRAM. And this part is usually used for data. So it starts from 0x0060, and can go all the way for a maximum of 0x0ff. This is the maximum capacity, all F's. So this is the maximum capacity of this SRAM. So SRAM is used for as a secondary storage. So the GPR are the only way we can communicate with the ALU. The SRAM are additional data. So you can see there are lots of values where we can store our arrays, a large message, some large data set. We can all place in the SRAM. It cannot fit in the 32 registers we have in the GPR. So this is why we have an SRAM. It's called the data space. So we have the GPRs, which are connected to the ALU, which are operational variables. We have the special purpose registers, which are the input output registers, IOs they call them. These are specific registers used for our settings, our specific operations. And then we have the SRAM, which has big data availability for us to use in our program. So sometimes also we have extended IOs. So instead of actually just having 3 parts in the 3 to 8, we also have this extended IOs in Atmega. Okay. So the extended IOs is going to be like this. So we have 32 registers, called GPRs, and then we have the 64 special purpose registers, or IOs we call them. Then we have an additional IO register. They are accounted for 160. So this is specifically for the Atmega 328, and we have 2048 bytes for the SRAM. If I want to look at the specific addresses of these parts, as we know, we started with, starts from 0x, of course 16 bits, and then we have this ends at 0x001f. This starts from 0x020, and then we go all the way to 0x005f. The next one will be 0x0060, all the way to 0x00ff, then 0x0100, all the way to 0xFFF. This is the maximum capacity. I will show you later that actually we don't reach this 0xFF since it's huge. We only have 2048 bytes, so this is actually, the number is actually much less. So now if I want to draw the memory, this memory, so we have the ALU, and this ALU talks to or takes inputs from the GPRs, and then it returns the value to the GPR again. Okay, sometimes I have some here some flags like the carry, the overhead, the 0 flag, and some other flags. This is a special register. This is the first special register we're going to take. It's called SREG, special register, and it has all of those bits, and it's found inside the IO part of the Atmega 328 architecture. So as I said before, we have the GPRs and we have the special function registers. Now we took 2 instructions to work with the GPRs, Now we're gonna go ahead and check further instructions that deals with the I/O part and the SRAM part. So now let's talk about how to read values from the SRAM and store values into the SRAM. So let's talk about SRAM data space. So concerning the SRAM, to load from it, there is an instruction called LDS, which means load from data space. And LDS, similar to LDI, it takes a register destination and a constant. This is actually a 32-bit instruction. We'll talk about binaries and machine language later. So K takes 16 bits. This means K is the address I want to load from in memory or data space. So if I draw it again, I'm not going to draw the extended IOs for simplicity. So we have the GPRs and we have the IOs and the SRAM. So let's say I want to go ahead and read this value is 0x0200. So let's say we have inside this address a value of 0x. Of course, the value inside is 8 bits since it's the data bus is 8 bits. So let's say we have 0x05 here, and I want to place it in a memory location. So I can place it in any memory location since RD, the D can be anything from 0 to 31. So let's say I want to read this value. So I do LDS R3. Look here, I can use less than 15 because the index of D can go from 0 to 31, and I do 0x0 to 100. So what happens is that it will take the value and store it in R3. This is very important since if I want to add something to this number, I want to do some manipulation using the ALU, the value should be in the GPR. It cannot stay in the SRAM and communicate with the ALU. All the values should go to the SRAM and from the SRAM to the GPR, and the way to do this is using an LDS instruction. Now I can, let's say we have, I'm going to do the same example, say 0300, and we have 0x0006, and let's say I do another load to R4 0x0300, and then add R4 R3, and what happens is that the value of the second one will be here R4, we'll get 0x06, and what happens is that 06 will be cancelled out and we will have instead of it 0x0b. So we did the same example, but here we loaded values from the data space into the GPR and added those numbers. Now R4 will have 0x05 plus 0x06, which is 0x0b. Okay, so reading from the memory space is very easy. You notice that we take the value from SRAM and place it in the register RD. Now I can do the same. I can actually store some values. So how can these values are in the SRAM? So another instruction is the Sts instruction. So Sts, store in data space. So Sts The way it works is as follows. We have STS K, RD. We notice here that a very nice feature of AVR instructions is that the destination is always on the left. So what's in RD will go into K. So in other words, SRAM of K will be equal the register RD. So same with LDI and LDS. If I take LDI RD comma K, we see that the K is going here, and LDS RD comma K, also the value that's in K is going into RD. Well, here we mean by this the SRAM of K. Okay, so let's now write a program. Let me write it officially. Write a program that stores 5 and 6 in locations 0x200 and 0x300. It's a very simple program. Well, actually, I need first to get them into my registers. I can use any register. I'm going to use R17, R20, X06, and now I want to store them into my location. So the way I use is STS, and I use R. This is my location, R16, X300, R20. So the value inside R16 will be stored in location 200. And if I draw my SRAM, this is the I/O, this is the GPR. So first, what happens is that, so number one, I placed in R16 0x05, so this is number one. Number two, I place in R20 0x06. Then number three, in location 0x200, I placed 0x05. This is number three. And in number four, I placed in 300 0x06. So STS takes this is the STS path into the data space. So this is how I can read and write from the data memory. Alright, so to emphasize more on the concepts, let's do a small program. Write a program that adds the content of 0x0400 and 0x0300 and stores them into location 0x0350. So first, here I have addition. So from this word I know that I need to read the values from the memory to the GPR. So if I explain more, this is the SRAM. This is the I/O. I have no use for it now. So I have 0x400, 0x300, the I/O. And what I want to do is add this value, whatever this value is. Let's say it's X. I don't care about the exact values, and I want to store them inside register location 350. So in order to do the addition, first I need to read the values into the register, the GPRs, add them, and then store them in the SRAM. So first I need to read the values. So number one, let's read the values. So I know do an LDS R2, 0x400 to LDS R3, 0x300. Now I can add them. Add R3 to R2. It can be R2 to R3, it doesn't matter. And the fourth step is actually saving the value into the location 350. So 0x350, R3, which has the value. So first I read the value. This is 1, this is 2. I do the addition. The addition here is done in the ALU. So this is step 3. And then 4 is actually bringing back the value into the SRAM.